It's really great to be back. I spent last year my sabbatical here, which was wonderful, 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 and very productive. And I do remember the wines before colloquia. So thanks for coming. Today I'll tell you a story of stellar forensics. As you know, supernova and gamma ray bursts are the most powerful explosions in the universe. You can see them over huge cosmological distances. But before we can fully exploit their power and potential, we first have to understand which stars give rise to them. And that's the theme of my talk. That's why I call it stellar forensics. We see the death very easily over large distances, but we have to work backwards like stellar death detectives to figure out what star or what stellar system died and how it died. This is an image that shows nearby supernova M51, a famous whirlpool galaxy. And the thrust of my group's work is to look at supernova basically in two ways. One, the explosions themselves, so the explosion properties, light curves, spectra, and so forth. And the second one is looking at their environments, looking at the habitats where they live and die to deduce and constrain progenitors give rise to them. So that's going to be the theme of my talk. But before I move on, I would like to point out my collaborators. So here on the left are the ones who are currently with me at NYU, and here are the ones who were at NYU and moved on to greener pastures. With me right now is Tyler, who is a postdoc with us in our group, who's here. I thought he would be here. Who also is here on Wednesdays. He's helping to organize the STARS meeting, so you've seen him around. Mark, who's here, who's a graduate student, and also whose work I will present today. Then you might remember Wolfgang Kerzendorf. He was here for a year. He's now faculty at MSU for astronomy and data science. And then Fed Bianco, who was with us as a postdoc, as well as research faculty at CUSP NYU, who's now at Delaware in astronomy and data science. And she's also the LSSD co-chair for the transients and stellar variability group and the science collaboration coordinator. And then, so I'll show their work. You will see their pictures again, and also my group were Brower, who's now a postdoc at Harvard, Yuqian, who was a graduate student, and Magda, who's now a graduate student at the CFA. I'm also collaborating with the Polymer Transient Factory. So, the theme of my talk is transients of various forms. And one of the players, one of the big surveys that already finished and has now a successor in Zwicky, a transient factory. That was Polymer Transient Factory, and I've been collaborating too, so I'll present some results there too. Okay, so let's just start really basic overview. Supernova are exploding stars. They're very brilliant. Their light output can outshine a whole galaxy. And of course, the radiation, or the energy that we see in the form of radiation, is only the smallest part. So the energy released in radiation is 10 to 48 to 39 ergs if you integrate the light curve over time. Then the kinetic energy is 10 to 51 ergs. So that's the value that a lot of the people who work on a galaxy feedback into supernova and stars and galaxy simulations assume. And of course, there the question is how that energy in detail gets released as well as incorporated into the ISM and so forth. So lots of interesting work in that field. So that's the value we use, but I will tell you about a very interesting kind of explosion. These are the GRBs, in general supernova GRBs, that produce 10 times more energy. So they're sometimes called hypernovae, but that's a misnomer. We call them Brilliant type 1Cs for a reason I will tell you in a second, and they produce 10 to the 52 ergs of energy. So they're very important, and I will discuss them in detail today. Now, there are basically two physical types of exploding stars. One are the white dwarfs. These are, of course, the 1As that we know and love, that we've been using for cosmology. And all the other types are due to a plethora of different kinds of massive star explosions. Now, you, of course, have heard about long-duration gamma bursts. These are extreme explosions that are able to produce jets at high accelerated particles at very relativistic speeds. And if you, on Earth, see them along the barrel of the jet, we will see a GRB, a long-duration gamma burst. And there, the gamma ray emission is huge compared to other supernovae. So it can be up to 10 to 51 ergs just in radiation. So that's why they can be seen over huge distances up to redshifts of 10, which we have. So these are really extreme explosions, and we know that they're connected to some kind of massive star, but we don't know which kind. And that's the theme of my talk today. So in general, it's actually an embarrassment to a certain extent in our field that we've had no direct progenitor detections for many interesting kinds and many important kinds of explosions. For type 1As, we use them nilly-willy for cosmology. They're very important, but we still don't fully understand which progenitors give rise to them, if it's a double degenerate system with 2 white dwarfs, or one single degenerate system with 1 white dwarf and another companion star. And we don't have a direct progenitor detection for 1As, but the same thing for GRBs. GRBs just too far away to do it directly, and the supernova I'll discuss today, stripped supernovae. So we need more indirect but informative ways to do stellar forensics, and I'll discuss that today. The other reason why we want to understand supernovae and GRBs is because answering the question about the progenitors impacts many other fields. Of course, one field that has come to the front stage of astronomy is LIGO. So LIGO has discovered many merging black holes that are much more massive than the black holes we know of in the Milky Way. So this is a plot from LIGO Virgo before O3s, before the current run. And it's shown the masses that LIGO Virgo measured, and then, of course, the final mass here after the merger. And in purple, for comparison, are the EM black holes in our own Milky Way. And as you can see, most of the LIGO Virgo black holes are much more massive than the ones we've seen in our own Milky Way. So that's been a big puzzle that has revitalized massive stellar evolution. So a big puzzle is how can you make such massive black holes in a binary? Because a lot of the channels that people had thought of before would lead to either mergers before the actual merger as a black hole. It would lead to mergers on the main sequence. So that's been a big puzzle, and one of the models that people suggested is the same one as for GRBs. And I'll discuss that today. But the main point is that in order to understand the LIGO black holes, we first have to understand the GRB progenitors. And of course, we'll work on that. So this is results from before O3. So in the meantime, LIGO has been amazing. LIGO Virgo, it's been finding black hole mergers almost every week. It's been a huge new window to the universe, a huge new population. And he's not here in the audience to either confirm or deny. But I believe that the masses they've been finding are as massive, are the same, if not more, than what's shown here. Partly because the distances they've been finding these new black hole mergers are huge. So in order to see them, they have to be very massive. So it will be great to see what they come up with after O3. But I would say the puzzle will only be compounded. So another reason, of course, why we are interested in supernovae and GRBs is that they produce most, if not all, of the heavy elements. They disperse them for sure, and some produce. And of course, the neutron-star merger, as observed with LIGO, the very famous one 2 years ago, also had an electromagnetic counterpart, the kilonova, that showed evidence for our process elements. So that's been an important topic, and of course, understanding supernova GRBs and other transits like kilonova will also help us understand the chemical enrichment history of the universe. Now, last but not least, they are important for cosmology. So SWIFT, which is a NASA satellite, was launched in 2004, and its dedicated mission was to find GRBs. That was like the whole mission. And it's because GRBs are so important, and they can be seen over huge distances, as I mentioned before, up to redshifts of 10, 8 or 10, so that's when the universe was only 500 or 600 million years old. I mean, that's pretty amazing. We can see the death of one or perhaps two stars out to these huge, huge redshifts. And of course, then GRBs illuminate and also ionize the early universe. So when people talk about reionization of the universe, GRBs can be a source, and there's been also discussion. And of course, they can be used as a very powerful tool for indicating star formation over huge, huge distances. But before we can use them as those tools, we first have to understand which stars give rise to them. In particular, if we use them over as star formation indicators of cosmological distances, are they biased or unbiased? Are they just trace star formation linearly or simply, or is there a certain bias towards other ingredients that are needed to make a jet? For example, low metallicity, as I'll discuss today. So that's a big question. So now that I've given, hopefully, some motivation for why it's important to understand supernova and GRB progenitors, let's talk a little bit more about the kind of zoo of supernovae. So type 1s are supernovae without hydrogen, type 2s do show hydrogen. So these are the spectra by which we use to classify them. So these are type 2s with the hydrogen bomber lines. Some of them show them in emission, so these are type 2Ns, and for narrow lines, so we think those are due to interaction between the exploding star and the circumstellar material full of hydrogen. And then there are these other subtypes, so bear with me here to go through all the different subtypes, but at the end you only have to remember these two subtypes. So type 2s are objects that show a little bit of hydrogen at the beginning, but over time show very strong helium lines. And actually Cas-A, which is a Milky Way supernova remnant that's very nearby, very well observed. Actually from its light echoes, we know we got actually a spectrum. It was like a little time machine. It occurred 300 years ago, but now the light has been bouncing around, is now coming towards us and has reached us. And from the light echo spectrum, we see it is actually type 2b. So they are important, they're out there even in our own Milky Way. So type 2bs show a little bit of hydrogen, but lots of helium lines. Type 1bs show no hydrogen or very little hydrogen. There's a lot of debate, but strong helium lines. 1bn can show these helium lines in emission. Then we think that's an interaction of the supernova with a helium-rich circumstellar medium. And then the 1Cs are basically the rejects of the classification scheme. They're defined by what they don't show, which is they don't show hydrogen, they don't show helium. And actually, they can be confused with type 1As, right? Type 1As are similarly defined, no hydrogen, no helium. I haven't shown them, but contaminants due to 1Cs in type 1A high redshift surveys is an issue. So type 1Cs are the rejects. They can, as I said, they don't show hydrogen, they don't show helium, they can show a little bit of silicon similar to 1As. And then in the last 20 years, this new subtype has emerged that are called broadline type 1Cs. So these show broad absorption lines. So for comparison, here's silicon compared to the normal 1C. And those are the only type of supernova connected with gamma ray bursts. So this is really important. Even when Stan Woosley or even my colleague Andrew McFadgen at NYU says, oh, these kind of supernova GRBs or 1Bs, 1Cs are stripped envelope. And I'll discuss a stripped envelope in a second, or what I call that. In all of these discussions, it's really important to remember that only broadline type 1Cs are connected with GRBs. So it's going to be a very strong clue. And why are these important? Well, these broad lines indicate very large expansion velocities, up to 20,000, some of them even 30,000 kilometers a second. So imagine you have multiple solar masses of ejecta moving at 1/10 of the speed of light. So that's a huge energy, a huge kinetic energy. And so when people infer kinetic energies, those are the ones with up to 10 to the 52 ergs. So these are the broadline type 1Cs. Since I grew up in Germany, I love compound words. So I will use broadline type 1Cs in the rest of my talk. Okay. So now what are the progenitors that we think give rise to these objects? Well, if you have, this is a cartoon of a pre-explosion star, a red giant, more massive than 8 solar masses, and you see these onion layers, which of course are not fully correct. There's a lot of mixing, so they're not stratified, these layers of different elements, and of course there's rotation. Matteo, of course, works on those objects too, so they're oblate, and so it's much more complicated, but the main point is that if you have such a star that has its outermost layers intact, the outermost layers of hydrogen and helium, and if that explodes, we will see a type 2, and we have seen such objects. So type 2s, we have pre-explosion imaging. Those are red supergiants. And of course, 87A, which was the closest supernova, was a blue supergiant, which was very exciting, very interesting. Now, the other types of explosions we think are from stripped stars. So if you have a star that has been stripped of its hydrogen envelope, the outermost layer, if that explodes, you will see helium. So we think that's what gives rise to 1Bs. And if you have the most stripped stars, the most naked stars, where there's no hydrogen and no helium, we think those give rise to the 1Cs and the supernova GRBs. Now, there are lots of outstanding questions still. For example, could you have hidden helium? It turns out stellar evolution, Mathieu can tell you much more. It's really hard to remove the helium layer because it's still very strongly bound to the rest of the star. For the red supergiant phase where you have this puffy hydrogen layer, you can cough and it moves away. But for helium, it's much harder, so people discuss hidden helium. I will not discuss it here today, but if you have questions, we can discuss that. And the other question, of course, is what are the stars that, in addition to being stripped, like the supernova GRBs, or broad integrals in general, what are the stars that then also give rise to the jets, as shown here? This is actually these hydrodynamic simulations by Andrew McFadden at NYU. So, and the reason for this question is is because long-duration gamma bursts are very rare. They're only around 1% of all stripped stars. So besides stripping, you need something else to make jets, as far as we can tell, because that's, again, we only see the GRBs if we are looking down the barrel of the jet. So what are the progenitor channels for stripping stars? Well, one common one that has been noted is if you have single massive Wolf-Rayet stars. So Wolf-Rayet stars, we've seen them in the Milky Way. This is actually a real NASA image. They have metallicity-dependent winds. That gives rise to mass loss. We have measured mass loss rates. We know the speeds around 1,000 kilometers a second. Again, this is a real image where we can measure that. And so that's one channel. However, it does make a prediction, namely that this can only happen at high metallicity. Because these metallicity-dependent winds are such that you need high opacity due to iron to really drive them. And so that means that if you want a lot of mass loss, for the most stripped stars, they have to be in high metallicity regions. Now, what about another channel? This is called the chemical homogeneous evolution channel, where you have a highly rotating star, where it rotates so highly, so much, that meridional flows basically take the hydrogen layer and take it into the core, and that's how you move the hydrogen, where you burn the hydrogen. So that would be the kind of chemical homogeneous evolution channel, and that has been suggested for LIGO. And this would predict that you would see this channel at very low metallicities. So the numbers people quote in the papers by Norbert Lange and Stan Woosley suggest up to 1/100th solar where that would happen. Now we have another channel here where you have binaries. Of course, binaries, as we know now, are very common since 2012 or so. I mean, there were indications beforehand, but since 2012 we have systematic surveys of stars and clusters in our own Milky Way, and they indicate that up to 70% of massive stars are in binaries. So binaries may have an impact, and one way to have an impact is stripping the star. So if you are a supernova progenitor here, you can be stripped, you can have Roche lobe overflow onto your companion star, and that's how you move your hydrogen, and even your helium. And this should happen at both high and low metallicity. And last but not least, another channel to remove the outer layers, what's called the common envelope ejection mechanism, where you have two stars again in a binary, but here you have unstable mass loss, and so you make an envelope around both stars. That's what's the common envelope, but then you eject it somehow. I mean, that's a big debate. A lot of people, Phil Chang, for example, who was a sabbatical visitor last year too, work on how the details work out. But that would also give you a way to remove the outermost layer of hydrogen, and that should happen both probably at low and high metallicity. So why is metallicity important? So not only is metallicity important because I will show you can try to measure the metallicity content, and each channel gives a prediction for what the metallicity behavior should be for that channel, but it's also it's important for the angular momentum content in the core. So it turns out for a lot of the GRBs, as we'll discuss, one of the ingredients is to have high angular momentum. And why is this interaction or this play between angular momentum and metallicity? Well, if you have different amount of iron in your outer envelopes, that would lead to different amount of mass loss. And if there's coupling between the outer layers and the core, you would also then have different amount of angular momentum in the core. So that's how the reason goes. And for GRBs, for all the different models, and of course Rosalba here works on one of the models for GRBs, which is potentially magnetar, so highly rapidly spinning neutron star that's also highly magnetized. In all of them, you need high angular momentum in the core to produce these jets, again, somehow. So that's setting the scenario. Okay, so now what about off-axis GRBs? So when we always talked about when we see the jets down the barrel along the line of sight, but what about the more common case, especially if it's a highly collimated jet like on this cartoon, what if we're off-axis? We should see those. There should be lots of off-axis GRBs out there, but so far we have had no conclusive detection. And I will, in a later part of my talk, I will suggest that we think we found very good candidates. And I will discuss how we're going to go about doing it. But some people think that this is a very important question. $1 million, that's a lot of money. Not so much perhaps if you want to buy in New York, but many other places, it's a lot of money. So where are the off-axis GRBs? So I'll come back to that later. Okay. But one prediction, of course, is that on and off-axis should be just a geometric effect, right? And so it should be random. And what it tells you about the habitats of environments is that they should be the same between on-axis and off-axis GRBs. So keep that in mind. Okay. So now let's talk about metallicity. So I know a lot of people work on metallicity measurements for stars. So I'll move here to talk about ISM metallicity. So when we talk about stars, we want ideally the amount of iron in the star. That's what gives us rise to the opacity, to the metallicity when it wins, and that's what's important for the GRB collapse bond and so forth. However, these are extragalactic objects. The closest supernova GRBs are at 60 megaparsecs. The furthest one is, as I mentioned, redshift 10. So what we are using is the observed oxygen abundance in the H2 regions at the position of the supernova. And these are the kind of funny units that people use, 12 log over H. And of course, oxygen is a very good tracer for overall metallicity. It's the most abundant metal, of course. And there's strong lines due to oxygen that we see in the host galaxy spectra that we can obtain. So there are many good reasons why we want to use oxygen. The other reason is that these are from H2 regions, and we do that for the supernova and try to observe the H2 region at the position of the supernova. And because these are short-lived stars, they won't move much between the kind of birth site and the death site. So when you look at the death site, it's a good indicator for what the conditions were at the birth site. Okay. So what's the state of the art? It turns out the devil lies in the detail, as with many things. I'll just briefly summarize what we do, and it is important. So we want to, again, observe at the position of the supernova GRB to probe the natal metallicity. A lot of people might not do that. So that's really important. So we want to use a large wavelength range to have a robust and uniform metallicity estimate, of course correct for reddening. We want to remove stellar absorption in the spectrum when it's necessary. Turns out A stars, right, they absorb hydrogen, but we want the hydrogen and the oxygen lines in the spectra of these host galaxies. And also we want to do a good job in uncertainty budget. So it turns out in the supernova field, it's still very much discovery-driven in terms of uncertainties and understanding them. People are a little bit laissez-faire on that, especially in the GRB side, not the 1A side, of course. There, it's very important. But we were the first to introduce, be very aware of how we deal with the uncertainty budget when we go from the flux measurements of your lines to the metallicity estimate at the end. And last but not least, if you know a little bit about the kind of metallicity field, you know that there are these kind of wars between different scales almost. And there are different ways. There's the photonization way, there's the direct temperature method way, but basically the point is that there are different scales, there's no consensus which one is the best, and they are systematically different. So what we've done is we wrote a code that we published in Astronomy Computing that's Fed-led, where we have a Monte Carlo-based code that includes all the state-of-the-art scales. There are around 13 out there. That does a good job in propagating the uncertainties correctly into your metallicity estimate. And here, just for visualization, I show you the metallicity estimates in these different scales based on the same data. And you can see how different they are. This is the kind of solar oxygen abundance. Again, there's some discussion what that number is exactly. There's the high value and the low value, so we just put in a bar. But the point is that it's really important to do these analysis in different scales to see if any trend you find is really physically true or whether it's an artifact of the scale. So that's what we propose, and that's what we do. I will show you plots where we use different metallicity scales to derive conclusions. And some people in the field don't do that. They just use one. Okay, so what did we do? So part of my NSF career work, I went out and obtained PTF, host galaxy data. So why PTF? PTF, back when it was operational, between 2012 and 2016 or 18, between PTF and IPTF, it's a galaxy untargeted survey. So that's really important. Basically, in traditional surveys, like when I was an undergraduate at Berkeley, traditional surveys had very small fields of view, so they would just choose which galaxy they will observe that will fill their small field of view. Because they wanted to harvest as many supernovae as possible, they would target galaxies that have the most stars. Makes sense, right? However, galaxies that have lots of stars, they have high masses, they also have high metallicities. So these traditional surveys were biased towards finding supernova in high metallicity environments. So PTF was different. It's a galaxy untargeted survey. It's a huge field of view, 7 square degrees. And so it was looking at various random parts of the sky and detecting anything that would go off independent of its host galaxy. So we had 100 stripped supernovae from that survey, and so I went out and took data for all of them. So I used Keck with collaborators, Palomar and Gemini through NOAO. It's a picture of me in the bowels of Palomar to show you that I was really there and looking, did my work. So given that, we compiled the first galaxy unbiased sample of 1Cs and broadline tapeworms from the same survey, found in the same unbiased way as GRBs, because GRBs are found in the same untargeted way. You have SWIFT that looks at 1/7 of the sky at any point in time, and we'll find a GRB. So it's not a targeted survey at all. Oops. So now you're awake, right? Okay. Java. Don't you love Java? Okay. So similar to, so the number we have, the objects we have, increases the sample that's been available for by a factor of 2. So also we carefully typed supernovae at many epochs with SNIT. So it turns out transients can change their IDs. And it's very interesting in itself why that happens. But what matters is that if we want to do this kind of work and we want to compare apples to apples, broadline type 1Cs with and without GRBs, for example, we have to make sure that the types are correct. And then what we did was we carefully computed the oxygen abundance and also other parameters for their environments and their host galaxies, such as star formation rates and masses. And of course, mass estimates are also very interesting if you're in that field, kind of what code you use, what uncertainties, if you get any uncertainties out of it. So that's a huge field in itself. But we try to be very consistent between the different samples we had. So we had 1Cs, the cousins, the broadline type 1Cs, and we compared them to literature supernova GRBs. So what did we find? So what we found is shown here in one plot. So what you see is the metallicity of the host environments of different kinds of explosions. So now in black, you see the PTF 1Cs. Here are the numbers we had. In blue are the PTF broadline type 1Cs. And then in red are the supernova GRBs. And you might wonder about kind of the small numbers still. So these are really rare objects. So far, we only have 10 or 11 supernova GRBs up to redshifts of 0.3. These are just really rare objects. And PTF, we worked hard. We have now 14 broadline type 1Cs in their volume. And then the normal 1Cs are kind of more common. But we found, and you can see right away, so it's a cumulative distribution function. Here's just a histogram in this one scale, is that the metallicity of supernova GRBs is very similar to these broadline type 1Cs without observed GRBs. So here in this case, the PTF broadline type 1Cs didn't have a GRB trigger, so that's why we call them just PTF broadline type 1Cs. And then, of course, these are the PTF 1Cs. So these are the ones that PTF found that have no broadlines. And we did this in kind of different scales. So this is kind of the different scales, Dobita et al., Kilian Dobita, Pitin Pago, Marleno et al. And so we found the same trend for all of them. Namely that the supernova GRB metallicities are very similar to those of broadline type 1Cs without observed GRBs. We also included various tests, the kind of survival tests include upper limits for some of these. So that's also important to really kind of use all the data we have, even upper limits. So what we find and what we think that these data tell us is that, first of all, there seem to be very different progenitors for broadline type 1Cs versus 1Cs. So even though the names are similar, they're cousins of each other, the host environments are very different. So we also take that to indicate that they also have very different progenitors themselves. So even though some people might tell you, oh, perhaps you don't know what you're talking about when you talk about broadline type 1Cs, 1Cs, just put them all in one bucket, the environments tell us a different story. The other thing we take away from this is now we've shown that supernova GRBs and broadline type 1Cs have similar environments. And what we take that to indicate is that we have now very good candidates for off-axis GRBs. So here is a cartoon, so where we think the supernova Gs obviously are the ones we see along the line of sight of the jet. However, the broadline type 1Cs, and they should be out there, these broadline type 1Cs are ones without the jet, with a jet, but we didn't see the jet because it was pointed away from us. So now we think we have a very good candidate, and that even these broad lines, as I joked earlier, some people just call them hypernova or something, or they put them all in one bucket. These broad lines are really important and may indicate a jet. And that's consistent with work we did with Jennifer Barnes. So Jennifer Barnes now is at Columbia, but before she was a graduate student with Dan Kaysen at Berkeley. What we did there with her was to do the first end-to-end simulation of a jet inside a star. So what we did is we took stellar evolution models similar to MESA. We put in a jet. We used Andrew McFadgen's hydrodynamic simulations to make the jet travel through the star. And then we coupled it with Sedona, which is a 3D radiative transfer code, and saw what kind of spectra you would get from the explosion as a function of viewing angle. So that was the first kind of end-to-end simulation of the exploding stars with a jet inside. And what we found was very surprising. What we found was that even if we look off axis, so this would be here where we, just goes this way, we look at this way, we still saw spectra that showed broad lines. So even off-axis GRBs showed the impact of the jet traveling through it, and I wondered why this happens. Because you would think perhaps if the jet goes through the star here, that's where it accelerates the ejecta, the stellar envelope. But it turns out in the hydrodynamic simulations, we were able to see that the passage of the jet through the star was causing lateral shocks. And those were moving out through the star and accelerating the stellar envelope as supernova ejecta and making these broad lines. So these broad lines, now from kind of data that we have with environments and also theoretical modeling work, indicate that there was a jet inside the star. So now we think we have a very good set of candidates. These are PTF broadline type 1Cs at low metallicity and high velocity. So I didn't discuss a little detailed velocity, but it turns out supernova GRBs, in my prior work, we showed that supernova GRBs have higher velocities in the spectra compared to broadline type 1Cs without observed GRBs. So those two things would be important. So at low metallicity and high velocities, those are very good candidates for off-axis GRBs. And now we want to actually check if these are off-axis GRBs. And one way to check is going back at very late times with radio, with the VLA, and seeing if the jet that was at the beginning collimated, so moving this way, over here on Earth, over time, even the most collimated jet will decelerate and become spherical, and you will have emission from the jet even when it was collimated at the beginning, and you will have that radio emission at late times. And so now we put in a big VLA proposal to go back to this PTF supernovae and see if we can detect it, if we can detect them in the radio. And if we do, that would be a very, very strong, very direct indicator that these were really off-axis GRBs. We'll finally find them, and I'm not sure if I claim that prize with David El-Azati, if he's going to be $1 million, but that would be really important. And this kind of idea of relativistic jets, I mean, that's a huge field, right? Yuri and others work on relativistic jets in detail. That is, a very important field that has these direct predictions of off-axis GRBs that we haven't found so far. So that's, again, has been quite an embarrassment. Now, in terms of looking ahead, there will be new radio surveys that will go deeper right away, and they will have huge fields of view. And so hopefully we'll find more of these off-axis GRBs as they happen with radio surveys. So with the VLA, we have to go back and point back in that part of the sky and go really deep. But with these new surveys, we can just survey the sky. So you will have time domain surveys in the radio. So now let's go back to these progenitors. We had this kind of chart at the beginning where they predicted at which metallicities you would find these progenitors if they were to occur in nature. So let's look at the single massive Wolf-Rayet progenitor. So that would predict high metallicity. So that would be okay for the 1Cs because we do find them at high metallicity. So single massive Wolf-Rayet stars are still good candidates, but they don't fulfill or they don't match with our data, which suggests that these occur at low metallicity in real life. So what about this highly rotating star which undergoes this chemical homogeneous evolution? Well, it did predict low metallicity, but very low metallicity, up to 100 solar. But we found was that the supernova GRBs are more around 1/3 or 1/5 solar. So lower metallicity, but not as low as this channel would have suggested. So we think that's not a good candidate for at least the supernova GRBs. Now, what about binaries? So that's, again, they would have them at both and low. So yeah, so they're still in the running for 1Cs and for supernova GRBs. And actually, from other work with OR, we showed that the rates of, in general, stripped supernova are so high. The rates for stripped supernova compared to core collapse are 30%. So they're so high that single massive stars, if they were really above 30 solar masses, cannot provide enough progenitors, just assuming a simple salpeter IMF. So we have many reasons to believe that binaries are the main progenitors for stripped supernova and supernova GRBs in general. Now, what about the common envelope ejection mechanism? That's still in the running for supernova GRBs. And the nice thing about this channel is that it would lead to a system that still would also have a high angular momentum up until the end. Because this ejection would happen so quickly, so very much at the end, so that the remaining kind of two stars that might merge or whatever they do after that, that would have a high angular momentum that you need for GRBs. Now, having shown you that metallicity is important, at least moderately low metallicity, other work by, for example, Dan Curley and so forth have shown that actually in general GRBs, when they look at, for example, GRB rates as a function of redshift, that those seem to be biased star formation indicators. So comparing them to normal kind of star formation indicators from other diagnostics like H alpha and so forth, or stars. So he concluded that GRBs do not trace star formation for nearby redshift, so less than 1.5, and that's completely consistent with our work where we show that we need moderately metal poor stars, so SMC, LMC type stars to make supernova GRBs. Of course, I should briefly mention that, so now, as you know, FRBs are very interesting as radio bursts. We have the discussion, what are the systems that give rise to them. And for a long time, we had only one host galaxy match, and that was actually a low metallicity dwarf galaxy as for supernova GRBs. So that was very interesting. A lot of people working on, for example, magnetars or supernova GRB kind of powering mechanisms were interested in FRB. So they were interested in that before, but they found now emboldened. But now there's been another case with a host galaxy association. That one is a high metallicity massive galaxy. So FRB is the verdict is still out with two objects. But there are many reasons why people have been interested in host galaxies of different kinds of transits. So now let's move one step back. People who work on galaxy evolution and galaxies sure know about the fundamental and a very important metallicity, mass metallicity relationship. And there have been a few papers in the literature that suggested that GRBs might lie below the mass metallicity relationship. So this is one paper in 2010 by Emily Levesque, who's now at UW. And so she showed with these objects that near GRBs, so these are GRBs with supernova down here, except one here, that they seem to be below the Sloan metallicity, mass metallicity relationship. So that was very intriguing, but also very puzzling. That would mean that the GRB knows about its host galaxy, and that it only chooses the ones that are off that metallicity, mass-metallicity relationship, and that was very confusing for many reasons. So we went back now, 8 years later with a much larger data set. We had twice as many supernova GRBs, and we did the same analysis again in these different scales. As you can see, the absolute values are different for metallicity in different scales, so you have to do it in these different scales. And what we found was that actually, yes, the supernova GRBs at 2 sigma are consistent with Sloan. So kind of this, and so here you can see by eye, and again, it will depend on which scale you use, right? The one here, MOA, shows like the largest difference. So in red are the supernova GRB mass metallicity relationship compared to Sloan, which is here in yellow. So depending on the scale you look at, you might find one specific scale that you perhaps would have chosen only, you would have got this result. But again, it's really important to do this in all various in different scales that are independent as possible, to see if you see a trend. And then for these other ones, you see that it's fully consistent at 2 sigma with Sloan. Given though with the caveat that Sloan only goes to a certain mass, it goes down to around 8.5, and many of the supernova GRBs are in lower mass galaxies because of this correlation between low mass, low metallicity for galaxies.
Is that why there's that apparent break in the number of sources, right? Around so around 10 to the 10 stellar mass. There's kind of nothing.
Yes, there are no supernova GRBs, but there's still 1Cs, right? The black ones are 1Cs. Yeah. So I mean, we think that's due to the metallicity preference, right? It's 8.5 or so in the scale. So above that, we don't see any supernova GRBs, and because of this relationship between mass and metallicity, if you go to higher metallicities, there would be higher masses, and we don't see supernova GRBs at very high metallicities. So we do different tests and get this result that within 2 sigma, it seems like they're behaving as Sloan galaxies to most extent. They don't have a certain kind of supernatural preference in some ways to certain galaxies, compared to the full galaxy population. Yes.
But following up on what Chiara just said, it's true that there is a preference for GRBs to lower metallicity, but what about the type 1Cs? So why you don't see a continuum of type 1Cs also in the gap? Why you don't see type 1Cs in the 9.5 log M?
So here?
Yeah,
there's some. So here these are the 1Cs that are black. They're the ones in black, so right? So here the ones in black.
It seems to be a gap.
Yes, so you mean the gap between, so I mean we find that the 1Cs do prefer high mass galaxies, which are also more metal rich, right? I showed you that earlier, but because of this, correlation between metallicity and mass, these two variables are correlated, right? And so if you find something that's at high metallicity, there will most likely be in high mass galaxies. So that's the other thing. So a long time GRB people said, well, this kind of trend that you see at low metallicity is just due to, it's a star formation effect. Star formation, turns out, happens very likely in dwarf galaxies, right? People like Catherine and others work on that. But remember, type 1Cs are also massive star explosions. So if it was just a star formation effect, you would have seen the same effect on 1Cs, and we don't see that. They are still tracing high mass galaxies, high metallicity galaxies very easily. Okay, so the next question you might have, given that, as you can see, the supernova GRBs and the broadline type 1Cs are in these kind of dwarf galaxies, so these are SMC, LFC type dwarf galaxies, what about the feedback that you would get from releasing 10 to 52 ergs in a dinky galaxy? So while I was thinking about that and trying to kind of collaborate with people, Chris here mentioned, so it was a Gotham meeting last year, that they actually had a paper already on that, so that was great. So here in Suedal 2018, they used FIRE2 to simulate a release of 10 to 52 ergs in a dwarf galaxy, and what they find is that it's just very equivalent to using 10 supernova at 1/10 of the energy. So kind of having one big explosion doesn't make a big difference. And in terms of the rates, as I said, they are much less likely than normal 1Cs. They're perhaps 10, if not 100 times less likely. So kind of the impact will not be kind of extraordinary, given at least their simulations. Okay, so I want to move on the last couple of minutes to mention a little bit more kind of current work on the transients themselves. So we care about software infrastructure. We have a website where we release not only our data and data products, but also code. It's freely available. We worked really hard on that. We have a GitHub repository. Mark here has worked on that too. And we have new modified templates for what's called the SNIT library. So SNIT is the state-of-the-art supernova classification tool that people use, which cross-correlates the spectrum of your transient with a library of known types. And of course, that relies on having a large library to begin with, and we've been providing those templates for the library in these various papers. So again, this is all available here on our website, also our code. As I mentioned, we have code for metallicity measurements. We also have code how to measure velocities. It turns out when you have high velocities in the 10,000, 20,000 kilometers a second, you have a lot of blending. So how you measure velocity is crucial. I won't go into the details, but we have code that's freely available that people have used to measure velocities in supernova and transient spectra. And so this is what you can see here is actually something that Fred made. So spectrum of truth. You see the spectrum of 90BW. It was the first supernova GRB. This is a nebula spectrum. You see all these emission lines, oxygen, calcium, and so forth. And it predicts and matches really well with all the skyscrapers in New York in the 1920s. It even predicts the next one right here. And if you take an image now, there are lots of skyscrapers. So that's our SNYU website. So it's had already big impact. People are using this templates to do fingerprinting correctly, supernova GRBs, 1As for cosmology. And as I mentioned, we've developed tools. And I'm preaching here to the choir, I think. But in the supernova field, again, it's a very discovery-driven, kind of the Wild West of things. There might be not as much appreciation as it is here. Okay, so now moving to kind of a larger view of the teeming universe of transients. We have lots of different kinds of explosions. So this is on the x-axis, the characteristic time scale of them varying, and then on the y is the absolute magnitude, absolute luminosity. And as you can see here, for a long time, we had these well-established classes, these thermonuclear supernova 1As. We can see the light curve shape luminosity dependence that we use to standardize them really nicely. So they're here, and then we have these core collapse supernova. But in many ways, they were just this very small subfield of this huge parameter space because the surveys back then were limited. They were limited to certain cadences. They were looking at transients with cadences of 1 or 2 weeks. So they found things that varied on time scales of 1 or 2 weeks. Now, in the last 10, 12 years, we had a huge explosion of different types because of these new surveys, PTF, pan-stars, there are lots of other assassin, and so forth. Now, Zwicky Transient Factory, we've been finding lots of other kinds of explosions in this parameter space going to shorter time scales, but also to higher luminosities. So one class of transients that I won't have time to discuss today are these superluminous supernovae. So there are 2 superlatives in their name, and these are explosions that are 10 times more luminous than 1As and up to 100 times more luminous than normal core collapse. So the big question in the field is what provides their brilliance, what is the powering mechanism, and what are the stars that give rise to them. I won't have time to discuss this, but we had a paper where we showed that these superluminous supernovae have similarly broad lines, very comparable to the broadline type 1Cs, if you look at the spectra lines, not the continuum. So that might be interesting for whatever powering mechanism you have. It has to make broad lines in these explosions. Another emerging field has been these kind of fast transients, and I'll discuss them in a second, that are in this kind of parameter space at very short time scales. And that's going to be, of course, important for LSST, the elephant in the room. It's the biggest optical survey, going to be online in 2023. It's going to be operational for 10 years. It will survey the whole southern sky every couple of nights and will produce up to 20 terabytes of data every night and give rise to millions of triggers and alerts per night. So we'll be flooded. There's a huge opportunity too, but we'll have lots of transients and also lots of other important science, cosmology, BAO, and so forth too. Now let's talk about these explosive exotica that we've discovered recently. So already with ZTF, so you can think of ZTF, the Zwicky Transit Factory, as kind of a precursor for LSST that's finding hundreds of thousands of alerts per night. And it's a public survey, at least half of it, because NSF gave money to them. It's an MSIP award. So the important thing is that they have really early light curves. So the cadence that I mentioned earlier, the cadence for ZTF, at least the community survey, is around 3 days. So much shorter than the 1 week that we had before, though longer than the kind of institutional survey that is intranight. So if you had lots of money, lots of spare money, you could be part of the very short cadence survey. But anyhow, even the 3-day cadence is very interesting because we've been finding explosive exotica. For example, this one is 2018 GEP that Tyler has been working on. It's a fast blue optical transient, or FBOT named. So it rises very quickly. Kind of the rise time compared to other broadline type 1Cs is very fast, just 5 days or so, and it's very blue. So you see the G minus R color, and then also the SWIFT data that we also had of other broadline type 1Cs, and shows you that it's very, very blue compared to the rest of the sample. And the spectroscopic ID that we got showed that it was a broadline type 1C. Again, these very interesting objects with these broad lines. Perhaps jet was involved. That's again, keep that in mind. But it had an additional component, which was this blue continuum that other broadline type 1Cs don't have. So we see that blue contribution both in the photometry and in the spectra. So what are they? So if you plot them in this rise time peak absolute magnitude, what I showed you earlier, but zoomed in now into a very specific parameter space, which is these really short time scales. Now we've been finding many other ones too. They're called fast evolving transients. So there's no color information to call them blue because a lot of these surveys, like Kepler even, so I show you Kepler data, even if the supernova talk, or pan-stars, or supernova legacy, or DES even, they didn't have color information, so they just saw that it was rising quickly, so they called them fast evolving transients. But in any case, if you plot them here on this diagram, and you also plot what are the ranges by which these transients would have been powered by nickel, which is everything below those dashed dotted lines, you see that many of these, including 18 GEP, were most likely not powered by nickel. Meaning that the nickel you need to make it so luminous would be much more in terms of ejecta than the total ejecta mass you have at your disposal. So they cannot be powered by nickel. And nickel is very, very common. Type 1As are powered by nickel. 1Bs, 1Cs are powered by nickel. For 87A, we saw the beautiful late time decline lines due to cobalt decay. So many transients are powered by nickel. But what about these? So that's an outstanding question. What else could you have? Some kind of magnetar that's injecting energy in very short time scales. Could you have interactions with CSM? Perhaps these stars do a lot of interesting things before they explode. They have perhaps eruptions where you have a little bit of CSM sitting there. Now the ejector is running into it and converting that energy into light. So could that be? So Hoedel suggests that. But then again, how do you get the broad lines for at least this object and its twin, which is shown here, 16 ASU? So that's a big outstanding question. This is a paper in TREP, so we don't have answers yet, but stay tuned. So other things we want to do to get ready for LSST is to think again ahead, possibly to look at brokers to identify outliers and anomalies. So as I said, LSST will reduce the data, will have difference images, and will then send out alerts, but they're going to be millions of alerts per night. So you have to sift through that. And there is an opportunity to have community brokers. So there are a number of them that a number of people have been thinking about, but we've been here at NYU and some people also at CCA have been thinking about a broker to identify outliers and anomalies using machine learning. So Shirley's group is potentially interested. And one way to do that is this Presto color space to identify rare and interesting objects. So what it shows you here is the change, how quickly it changes in the blue band as a function of color. So as I mentioned, this one earlier, 18 GEP, which is right here, was a blue fast evolving transient. These are interesting transients. Other things that are fast and blue are infant supernovae. So supernova caught right after explosion, both for 1As and for core collapse. And those are very interesting objects because a lot of interesting physics about the progenitors is encoded in the early light curve. So that's kind of the emerging field right now, is to go after infant supernovae. So that would be another great way to discover them quickly and then organize follow-up resources. Because remember, LSST is only for photometric survey, and you have to, call up your friends on spectrographs or have access to dedicated spectrographs to observe objects, and you want to only observe the ones that you think are interesting, right? Given the huge number of objects that will be announced. So this would be a great way to identify rare and interesting objects in this kind of color space, and so this work is being led by Fed and Tyler. So the other way to think ahead, and that's where Mark comes in, is to think about data-driven IDs and machine learning. So as I mentioned, this kind of classification speed based on spectra goes back actually all the way to the 1940s with Body and Minkowski, where they had limited data sets and, as far as I know, no machine learning expertise. So let's rethink the kind of classification scheme, and that's what we've done, that's what Mark has done in his paper that just came out this year. In a way such that it's more physical, that the supernova classification scheme is more physical in the sense that it's continuous. So remember, the kind of classical one is hydrogen, no helium, right? I mean, stars are not like that. They're not step functions. There's different amounts of hydrogen layers, different amounts of helium layers. So we should have a classification scheme that captures that physical continuous distribution of outer layers. So Mark came up with using principal component analysis to see, first we found that up to 70% of our data set was to be reconstructed using principal component analysis, and then he used support vector machine to show you here these regions, and we found that using this PC1 and PC3 coefficients for these eigenspectra, show us really nicely where different types of objects live. So here you have the 2Bs, the 1Bs, there's some distribution, right? So we show you here the average, this one standard deviation, and for the first time we have now a quantitative way to classify supernova, not just, oh, no hydrogen, and some people debate what does conspicuous lines of helium mean? And it's all by eye in a certain extent, or whatever SNIT tells you in certain ways. So this is the first time we have a continuous annotation, and also for transition objects. And we can really, for the first time, quantify outliers. Because we can say these are objects that are 2 sigma away, now that we have this classification scheme. So I will finish here saying that what we found also is when we did this as a function of time is that 10 and 15 days have the best separation between these different subclasses. So what it tells us is later is better. So if you want to follow up your object, the best time to do spectroscopic classification is around 2 weeks after max, because that's when you can differentiate most easily between the different types. So that's good. So we don't have to scramble right away. We have 2 weeks to get our spectrographs online. So I'll just finish here saying it seems like future is super bright. We have Zwicky already producing lots of data. LSST is around the corner. 2023 is, seems closer as you think, right? And when you look at mirrors, JWC hopefully will be launched in 2021, hopefully. And there would give a great opportunity to look at very large redshift explosions, perhaps even the first explosions in the universe as POP3 stars. That's one science team I'm on. And perhaps in the very far future, though we should ask David here.
2025, we're the budget on schedule, not such a far future.
Okay, not far future.
Pretty soon after JWST.
Okay, so lots to do. Okay, so this is my conclusion. I hope I've convinced you that we still have this very fundamental question that impacts many fields, which is what are the progenitor of crucial kinds of stellar explosions? One way to look at it is to look at host galaxies, might tell us about the populations that give rise to these explosions. We found that these 1Cs and their cousins, these broadline type 1Cs, seem to have very different progenitors because they prefer different environments. That supernova GRBs seem to come from moderately metal-poor stars that are more massive. I didn't have time to discuss that, but we have indirect ways, evidence that these are more massive, that were in binaries. So we think we found for the first time very good candidates for off-axis GRBs. These are these PDF broadline type 1Cs at low metallicity that we're going after. And these broad lines might tell you that these transients hosted a jet that then you see the imprint in the spectra. And the future is pretty bright, if not busy given LSST's deluge of data. So I think a really exciting time to do time domain astrophysics. But we do need to tool up and use new tools to think about classifying supernova and identifying transients of interest. Thank you.
Okay, any questions for Maryam?
Yeah.
So you mentioned that you were following up some of these candidates with VLA or looking for.
Yeah, we put in a VLA proposal because we would have to go pretty deep.
So would future radio observations help, something like NGVLA or SKA?
Yes.
Or would other things happen before then that would be more useful for you? Like,
No,
what are the
this would be
timescales?
really next generation VLA would be great because it would be more sensitive, but also have a bigger field of view. So then you would get your transients, your survey basically for free. Right now with VLA, we have to go back, right? That spends a same amount of time on those parts of the sky. But off-axis GRBs should be happening. You would actually not only expect to see them years after, which is these off-axis GRBs, but also kind of orphan afterglows where the jet is not completely 90 degrees pointing away, but a little bit. So you miss the GRB, but you still see afterglow emission.
Yeah, Scott, are we ready for LSST? Actually, two are we ready for LSST questions. One, do we have the telescopes we need to do follow-up, and where do you see the biggest gap? And the second, with archives. Right now we have, 30 different archives for different experiments and observations. And NSF and NASA and DOE all have different archives. Do we have the right structure for archives?
Okay, so the first one, yes, there's a huge gap in terms of spectroscopic follow-up facilities. So there's some discussion, for example, with the ones that are already planned. So DESI, for example, and other things like perhaps Sloan 5 to use the spare fibers, but it would be kind of on an only subset of LSST. And for DESI, for example, OR is actually part of the transient group there. They will only target 1As to get the host galaxy redshift. So that's going to be one aspect for cosmologists. Perhaps the loudest voices, the most kind of input there.
They're DOE funded.
And they're DOE funded, so they're really interested in one number, right?
You have to convince DOE that you're consistent with your mission.
That's right, that's right.
So
there are many,
the DESI people had almost no choice.
Yes, that's right, especially once you then took over to fund it. Yes, so there are other ones too where kind of spare fibers might be interesting, but so far, there was a huge committee by NREO to see if we have follow-up resource for LSST. They all have these beautiful recommendations. All the work is out there. You can download it. But in terms of kind of actually putting in money to have either a dedicated facility or making it happen, I think we're very limited. So whatever we can to do photometrically, to identify photometrically what the interesting classes are, that's going to be really important. And that's what people are working on. Renee Slojek had a plastic meeting that was basically a challenge to try to classify based on light curves only. And turns out the 1Bs and 1Cs are the tricky ones. Now for the archives, so that's a very good question. I don't know as much about that, but my impression is that we're trying to, so LSST itself is getting ready. That's what I've been told. Melissa Graham, she's the data management person, so I think they kind of just 30 seconds. So for them, the challenge is they're getting the data from the telescope, and they have to do subtractions. So every 30 seconds, there's a new frame taken, and then every 60 seconds, they have to do the subtraction and send out the alert. So that's the kind of mandate they have. And so they think they're ready for that. But what we're not ready is kind of as a community, what we're going to deal with, how we're going to deal with the deluge of data. There are now already brokers that are running on ZTF. So ZTF is a great forerunner for that. Sri Kulkarni first called it as a kind of competitor, but then they get 1S7 and it became the precursor. So ZTF is already a great way to try things out. So some of the brokers have started running on it. Tyler and others have also started working on the ZTF stream, so to get ready to how as a community you can ingest those data. There is also a separate call for a general kind of what's called schema, scalable cyber infrastructure. addressing multi-messenger needs. So that's a whole discussion with LIGO and IceCube and so forth. So that's also in that context, how we're going to deal with large data sets. And so there have been, I guess, 9 institutions awarded money by NSF, including LCO, the Cumbres Observatory, where we're part of GSP, the Global Supernova Project, to work on that, to get ready for 2023 for that. Matteo.
Mary, you mentioned that superluminous supernovae show the presence of broad lines, similar to supernovae 1C with broad lines.
That's right.
I was wondering if you can comment a little bit about similarities and differences between the environment, galactic environments for superluminous supernovae and broad line 1C with associated GRBs.
Yes, good question. So the superluminous supernovae I discussed were these types that don't show hydrogen and helium. So there are also superluminous supernovae that show hydrogen. So those are the type 2 ends actually. So the ones I'm talking about are without hydrogen. And they also show similar environments, very comparable to supernova GRBs in terms of low metallicity. They seem to be actually at even lower metallicity, slightly lower, depends on the scale you use.
We believe it's a continuation of the same engine phenomenon.
That might be, yeah. So it could, whatever you have, be it a magnetar. I mean, you know, so for example, Gensler has, Metzger has kind of a unification scheme where you have a magnetar that can both make a supernova GRB or a superluminous supernova depending on the magnetic field and then the time scale at which it decays. So whatever, if they, I mean, the observational evidence that they're definitely related.
So I know we have more questions, but I think you should save them for Flatiron on Friday. So let's thank Maryam again.